Hello class, welcome again to Chapter 3, Derivatives. The focus here would be chain rule. Chain rule, as the name says, is something like a chain connection. Right? And we can say that the chain rule is derived from the idea of composition of functions. Now, composition of functions, if you recall, you remember this F circle G notation? That's the crisp notation for f of g of x. What it means is this g of x is composed inside f. So g of x is composed inside f. In other words, g of x is substituted inside f, right? Composed. So technically we have f of x and then we have g of x. We have two functions. And when this function here, if that gets replaced for x in the function f, that is composition. So if you look at the order f circle g, it is the second one, the g, that goes inside f. And the idea of composition is used to derive the chain rule for derivatives. And so I'll give you this breakup here. Now, if we had y to be a function of u, okay, and u in turn was a function of x. Okay. So let me just write that explanation quickly. Y is a function of u, and then here u is a function of x. So you can see that u is the common connection between the two, isn't it? So if I want to write y as a function of x, I have to go through u, right? And so when we say we need to find dy over dx, you know that u is the common connection, and because y and u are connected in the first function, you can split this dy over dx as dy over du, right, for the y, times, this is u and x, so you can do du over dx. So you can kind of see like the du and the du cancelling off, leaving us with dy over dx. So that is the concept or the idea of using composition to find the derivative, and that is your chain rule. Okay, so let me give you an example here for this type, and then I will give you the other version of the definition as well. So if I had y equal to 3x squared plus 1 the whole squared, okay, say this is what is given to us. You know y is already written in terms of x. But if I wanted to use the chain rule, okay, this looks complicated, right? So we use chain rule to kind of uncomplicate these things using composition of functions. So this needs to be decomposed, which means break into two functions so that you can compose one function inside the other. So what we do is, again, this is coming from our algebra. So I take this information here and I need the other information here. And if I can make this information go inside this information, this function, then I will get back the y, right? So then think about it. What can be done? Because this is like an outer shell, right? The square. So if you think about this strategically, I can write this as x squared because you want to replace the x with whatever's inside. So that's going to be my 3x squared plus 1. So if I can compose the 3x squared plus 1 inside this x squared, wherever x occurs, I plug that in, I'll get back my y. Therefore, I decomposed the given y into two parts, right? And so we have this and this. Now, instead of x, because there's too many x's, I'm going to call this u, so that I replace the u with the 3x squared plus 1. And you can kind of split this up and say, okay, then let y be equal to u squared, and u in turn will be 3x squared plus 1. So that when I compose this u inside y, then I get back my original function. So the whole idea is to do the dy over dx in this split form, dy over du times du over dx. So let's look at dy over du. So y with respect to u, that will be 2 times u times du over dx. So u with respect to x. So that will be 3 times 2x. Okay, that's plus 0, right? This whole thing, because derivative of 1 is 0. So technically you have 2u times 3 times 2, 6x. You can't have the u and the x because you want the dy over dx ultimately. So replace your u with what it is, what it represents. So I have, let me just collect these all. So this will be 12xu, and in the place of u I plug in 3x squared plus 1. So something that is complex looking as this can be arrived pretty easily if you split them up as two functions by decomposing it and then taking the derivative individually and remembering to replace the u in the end, because you can't have two variables there. You want them all in terms of x, because that's how it's defined, and that's how we get our chain rule. So you are going from, you're kind of linking the two. That's the chain part. Okay. Now the other notation that we can give this is going back to the f circle g notation, which is basically f of g of x. So if I wanted to do the f circle g prime, right, the derivative of this, that will be the derivative of f prime of g of x times g prime of x. So what we're saying is we took the derivative of f, that's why you get the f prime, right? For this function, this whole function, you take the derivative of f. And then g of x is also another function inside, so you multiply it by the derivative of what is inside. In fact, if you come back to this example that we saw before, right? So if you take this, y equals 3x squared plus 1 the whole squared, if I were to reconsider taking the derivative of that, so let me write that like this. 3x squared plus 1 the whole squared, because this is already in the composed form, right? So that's why I wrote it already as f circle g. So if I were to do this, okay, then it is the square part that is outside. So I'll have to do that first. So that's 2 times whatever is inside, keep it as it is. It doesn't matter what is inside it. So that's going to be 2 minus 1. So I just applied the power rule, right? So 2 times x power n minus 1, that times the derivative of the inside, because that's g prime of x, that's inside, right? That's what is inside. So 3x squared plus 1, so the inside would be 3 times 2, 6x plus 0, right? And this is what we got as 12x times 3x squared plus 1. And we did the same thing, but then when we split it up, it was a little manageable because you could see them individually. But when they're all together, what happens is we try to use the idea of composition of functions. So we don't have to decompose necessarily. We can just keep it the way it is and just remember to do the outside of the function first, the derivative of the outside first, and then times the derivative of the inside. Okay. So then that is what I'm going to indicate next. So we're going to use this inside-outside rule. Okay. So let me write this as a hint. Inside-outside rule. For chain rule, of course. So let me write that also. Now if I had dy over dx, and I had something inside and something outside, it needn't necessarily be a power, usually it will be, but it could even be a radical, right, which can be rewritten as a power. But if you had something like this, what we're saying is you need to find the derivative. So I'm showing you the d prime, the derivative of the outside happens first times the derivative of the inside. When you take the derivative of the outside, take note to leave the inside as is, because you're not touching on the inside. Don't touch, so leave it alone, okay? And then you'll only focus on the outside, which is what I just illustrated. Okay. Now we'll do another problem, and we'll try to understand the outside inside hint. Find dy over dx, and we're given y equals sine x squared plus x. Alright, so y is written in terms of x, but y is looking complicated because it's a composition of two functions. So the very first thing we want to understand is which one is outside and which one is inside. Okay. So this sine function, sine of something, right? Sine of an angle. So sine function is the outside, and this x squared plus x would be the inside. So now I have to do the derivative. dy over dx says derivative of the outside. What is the derivative of sine? Derivative of sine is cosine. Okay. So, and we said leave the inside as is. So leave it alone. So derivative of the outside is what we just did. Leave inside alone, which we did. We didn't touch the inside. Now it's time for us to focus on the inside. So the inside is x squared plus x. So the derivative of x squared is 2x plus derivative of x is 1. And that will be the derivative of the inside. That's it. Now we need to collect them all. There's an equal sign there. We want to throw the 2x plus 1 in the front so that the cosine has the x squared plus x following the cosine function itself. And that makes it easy for us to kind of see how they are spread out. Otherwise, there's a confusion whether this 2x plus 1 is part of cosine or not. So to clarify that, I just throw that in the front as a coefficient. And that was it. So derivative of outside times derivative of inside. If we were to split this up by decomposition, then what we would do is we have y equals sine u, because that's my outside, right? Y equals sine u. And then the inside, I would call it as the u. And then this would be dy over dx split up as dy over du times du over dx. And you'd get the same answer. You can actually use it as an exercise to verify that. Let's move to the next question. Find dy over dt. Y is tan 5 minus sine 2t. Okay. So we have, a lengthier expression, I should say. So let me write this out one more time so that we could identify the outside and the inside and so on. Now remember, the way we work through this is we start from the outside and work inward, okay? So if you can have multiple insides. So you can go from the outer inside to the innermost inside and so on. So in that sense, there'll be only one outside, okay? And I'd like to call this tan, of course, as the outside. And then this entire thing would be the inside, because that's the outermost inside. And then we have, I was looking for another color. Then we have this, right? So we have the inside. And then we have the 2t, which is inside one of the functions. Innermost, I would say, in this case. Yeah. So now we can go ahead and take the derivative. dy over dx will be derivative of the outside. So derivative of tan is secant squared. Secant squared of this entire function, so leave the inside alone. Okay. This is derivative of outside times derivative of the inside. So that's going to be, always write them in parentheses because you can have multiple terms. So derivative of 5 is 0 minus derivative of sine is cosine 2t, okay, times, and by the way, that was the derivative of the inside, times the sine 2t, right? So in the sine 2t, you're only focusing on just the 2t because your function had an innermost expression there. And so derivative of 2t is just 2, which is the last derivative of the innermost. You can have multiple layers, you just want to watch out for it. So I showed it to you in 3 parts here. Now let's shove them all together. So the 2 comes first, the negative 2 cosine 2t times secant squared 5 minus sine 2t. Make sure that you arrange them all in an intelligible order so that we have very clear expression indicated. Now for cosine 2t, make sure that you put that in parentheses because your cosine is a double angle here, right? Because we have the 2 times the t. And the variable here is t. So I just discovered that I made a mistake here. I wrote dy over dx. I should have said dy over dt. Okay, that's a classic example of how we can be fixated on these variables y and x. But here it was about t. And so in your homework, it will be quite sensitive if you wrote it as dy over dx. Even though your answer was written right, it will still be marked wrong just because the variable was incorrect. So watch out for that. Now we can have the chain rule, wherein you are basically bringing in a power rule and chain rule together. So there are some rules when we talk about chain rule that can happen there. So we said usually it's derivative of the outside times derivative of the inside, but we just saw that we can have several nested insides, and so this chain rule has to be repeated if there are several nested insides. So I just want to write that down here. Okay. Chain rule is repeated if there are several nested, you know what is nested, right? One inside the other. So several nested insides. Okay. And then we also see that the power rule of the derivatives, right? The power rule plus the chain rule will be a power chain rule. And I'd like to show you some examples to illustrate that. Okay. Now we know that we always want to get from, if you're using the composition of functions, we write y in terms of u and then u in terms of x so that we can find the derivative of y in terms of x. Okay, so we go through that. So here is a case where the power chain rule is basically coming from these 3 parts, the y, the u, and the x. Okay. So then we'll do those kind of examples here. Find dy over dx, and you'll be given y in terms of u, 6u minus 9, and then u in terms of x. As we see here, it is half x power 4. So we know that dy over dx will be dy over du times du over dx. Okay, dy over du, I just want to write it a little more explicitly. So the y, I'm replacing it with 6u minus 9 Again, this 9 and the A and all these things are always to be watched out for, because we don't want to misunderstand our numbers and letters. Okay. Times d over dx, du over dx, and u is replaced by half x power 4. Alright, so this will be 6 itself, right? It's with respect to u. So 6 times derivative of u is 1, and 9, the derivative of 9 is 0, times, this will be half times 4x cubed. And then the half, can reduce. 6 times 2, 12, 12x cubed. So there will be problems where you'll be asked to decompose into y and u, or they could give it to you like this, the y and the u separately, and you'll be asked to find the dy over dx. So here comes our next one. Dy over dx, where y is square root of u and u is sine x. Now, square root of u, that can be written as a power, u power half. Now we're ready to. So it's half u power half minus 1, n x power n minus 1, times derivative of sine x is cosine x. Half minus 1 is negative half. So 1 over 2 u power negative half times cosine x, and the negative half can be brought down, so it will be 1 over 2 u power half times cosine x. That in turn is 1 over 2 square root of u, because u power half is square root of u. And one last step where you have to replace the u. So u is sine x, so I'm going to come back here and say, okay, that's going to be 1 over 2 square root of sine x times cosine x. Again, if you want, you could shove them all together so that it could look like this, which is your dy over dx. Okay, so if it came to you in the decomposed form, you write it like this. If the same problem came to us, like say find dy over dx, and they said y is square root of sine x. I'm composing the two so that your y is written in terms of x. If this was what was asked of us, we have to first write this y equals square root of sine x as sine x power half, okay, and then identify this to be the half, the power. The power is outside, and of course what is inside is the sine x. So you have to take the derivative of the outside times the derivative of the inside. So that will be half, leave the inside as it is, half sine x power half minus 1 times derivative of the inside would be cosine x. Again, let me show that part to you here. Derivative of outside leave inside, inside alone. Can't insist enough on that because we feel like we have to work on it right away. No, we are giving it its turn because we do multiply by the inside, the derivative of the inside. Alright, so we are doing this using the outside-inside rule, and that will be sine, so half sine x power negative half times cosine x, and you can already see If it's a negative half, then I can bring the sine x to the denominator. Flip the base, change the sign. Cosine x, which is the same as having cosine x and the 2 square root of sine x in the bottom. So I ask that you become, quite familiar with both types and be flexible in both approaches. Derivative as a composite function, where you have the u coming in the picture, or using the outside rule, and then going further with that. Okay, we'll do some more problems. And u is 1 over x plus 7x. So you can always go back and reference our derivatives of trigonometric function section, where we learned about the different the derivatives for the different trig functions. And so for this is negative, so you can bring the negative out. So derivative of secant u is secant u tan u. That's coming from the rules, from the derivatives. That, and then here I can think of this 1 over x as x power negative 1, isn't it? Wherever possible, try to rewrite it as a negative exponent, and if that was the case, then you can simply use the power rule, and you won't be forced to use the quotient rule, because in this case that will be totally unnecessary steps there. Alright, so x power negative 1, so that's going to be negative 1 x power negative 1 plus 7, because derivative of x is 1. Again, if it is a little too fast, I want you to slow down, pause the video, and please work it out on your own. We've done the derivatives for a long time now, so you know that I'm doing that. So just pause the video and slow down for your sake, complete it at your end, and then come back to catch up with the other steps. Okay? You don't feel that you have to go in the exact pace of the video. You can always pause and take the time you need to understand the problem. So that's negative, 1 is negative, so it's x power negative 2 plus 7. Negative secant u tan u times negative 1 over x squared, because again, the negative exponent, I want to change it to a positive exponent, for which I have to flip the base and change the sign. So things are looking good here. The place where I need to fix this is the u, because we have to replace the u. But before I do that, I want to move this expression to the front. So that will be 7 minus 1 over x squared. Right? It's just looking appealing when you write it that way. And then there is this negative secant u tan u. So I can put it out here like this, okay? And then secant u, what is u? U is 1 over x plus 7x. Tan 1 over x plus 7x. I know it looks incomplete for some reason, because you have that huge expression following the secant and the tan, but that's the angle there. And you don't have to worry about expanding it or doing anything to it. Just leave it like that. The only other way to simplify this would be for me to think of it, for me it seems like we could absorb the minus, in which case it would be 1 over x squared minus 7, and then 1 over x plus 7x tan 1 over x plus 7x. So these are the two variations I can think of to this problem. Now, without going too deep into simplifying, because the purpose of simplifying is to make it crisper looking or for reducing purposes. Right now, It doesn't really make it look any crisper if you were to combine them. So this looks perfectly fine. Okay, we'll look at another type. Because the y is written in terms of x, and it looks that in that format, that complicated, where you can't directly use the power rule. You use the power chain rule in this case, and so use the outside inside technique. dy over dx. Outside is the power 5, so 5 times 2x plus 1, power 5 minus 1, which is 4, times the inside. The derivative of inside will be just the 2. 2 plus 0, so it's just the 2. That's the derivative of the outside times the derivative of the inside. Alright, now shove them all together. 5 and the 2 will be 10. 2x plus 1 power 4. Okay, what about this? Again, no problem, because we are the outside is the power in this case. I'll just write it here one more time so I can indicate the outside and the inside. Okay. Four minus 1, 3 times the inside, and for the inside it will be just the x, right? So focus on the x, so that's going to be, it's only the inside here, this orange part. That's going to be 2x over 8 plus 1 minus, this is going to be considered as x power negative 1. Right? So negative 1 x power negative 2. We just saw this, so I don't have to explain in much detail here. Derivative of the inside. And I always like to put the parentheses around them because you have two things that you're multiplying, and these are two huge expressions. So here I can see the 2 and the 8, 4. Simplify all of this. What we get is x over 4 plus 1 plus 1 over x squared. Yeah, the negative and the negative. So that times, and then we have the 4 here, so I'll put the 4 in the front here, and then I'll have x squared over 8 plus x minus 1 over x power 3. Again, you can leave it as, product of two separate things, or you could shove them together by throwing the 4 first, then the expression, and then the expression with the power. I don't think your homework answers will be too picky on that, but you can never tell. So always go by the instructions, go by the sample problems to see how they wanted the presentation to be. Secant of tan x. This is interesting. So let me write this out once again. Take a moment, you can pause the video and identify the outside and the inside functions yourself. So we now have dy over dx derivative of secant is secant x tan x, but here instead of x I have tan x itself. So secant x tan x, this is the formula for the derivative of secant, but we want to keep the inside as it is because we do not want to tamper with the inside. So it looks really complicated, but you're just blindly following the instructions. And then you have to multiply it by the derivative of the inside. The derivative of tan x is secant squared x. Put the s properly. And so that makes it the derivative of the inside. So if I were to write the answer, really there's no simplification that can be done, but I just want to throw the secant squared x in the front times secant of tan x and tan of tan x. And that's our answer. You have x squared sine power 4x Ooh. Okay, cosine power negative 2x basically is 1 over cosine squared x. Okay, you have something like this, no problem. I only have to remember that you do have to remember to do the chain rule for this one separately, because you have two separate terms. Okay, here also chain rule, but before you use the chain rule you have to use the product rule, isn't it? So we have plenty of things to do here, so I'll say chain rule plus product rule. So I'm going to remove that part here. Just for convenience, we can do them all in one shot, but again, only for convenience sake, I want to just look at the x squared sine power 4x so that you'll have a close-up, a zoomed-in view of what I'm doing. So that you can treat this as u and this as v. And the product rule, uv prime, is u prime v plus v prime u. So in this case, derivative of x squared sine power 4x will be u prime v, u prime is 2x, times sine power 4x, plus v prime. You look at v prime is sine power 4x, which is the same as sine x power 4. Okay, so sine x power 4, that's why you use the chain rule. So there is the product rule that we used, but within that we have the chain rule. So I'm going to use a different color to show what happens in that chain rule part. Okay. So sine power 4x is the same as sine x power 4. So the chain rule says do the derivative of the outside times the derivative of the inside. Derivative of sine x is cosine x. And so that's what I'm going to bring in here back into my step. And I'll say, okay, that will be v prime. So 4 cosine x sine cubed x, right? V prime u is x squared. So that is my derivative of x squared sine power 4x. Let's clean that up a little bit. 4x squared, we want to bring the x squared to the front so that we have cosine x sine cubed x. You got that? Then let me zoom in on the x cosine power negative 2x. Now you can also see this as x over cosine squared x and do the quotient rule, but we've seen that the quotient rule is usually challenging for us because we've got too many terms to keep track of. So I'm going to call this as u and this as v. uv prime is u prime v plus v prime u. And so derivative of x cosine power negative 2x will be u prime, which is x, so u prime is 1, times cosine negative 2x plus v prime. V prime, once again, if you do it by the side, we see that that will be, where are we? Cosine power negative 2x is the same as saying cosine x power negative 2, right? The outside power. So that will be the chain rule would say negative 2 cosine x negative 2 minus 1 times derivative of the inside, which is negative sine x. Derivative of cosine x is negative sine x. Okay. So if I were to clean this up, I get this negative and negative will combine, so I get 2 sine x cosine, that will be negative 3, right? Negative 3x. So come back and insert it. Plus 2 sine x cosine negative 3x. That's v prime u, so times x. Okay, we'll collect all of these. dy over dx is equal to the derivative of first part, x squared sine power 4x, plus the derivative of x cosine power negative 2x. So we did each of them separately, so we're going to bring them all together. You could have done them all in one step, as I mentioned before, just for clarity's sake, that we have them very detailed here. And the x, I'm going to bring this 2 and this x in the front. Sine x cosine negative 3x. U prime v plus v prime u. So remember to multiply by the times x in the end. And so this will be your answer. Actually, it looks it looks again complicated, but you have actually found the derivative here. I hope you'll appreciate that I'm throwing in a number of questions here and solving them for you. It doesn't work in most other sections because we'll have multiple concepts to discuss within one particular section, but here our focus has been completely on chain rule because this is such an important rule. It is going to be an unwritten rule henceforth, that whenever you have this, the chain rule kicks in along with the other rules that we have. And this is the case with the rest of your calculus journey. And therefore, it's worth giving this the time it takes because it really matters. Y equals t times tan t. Okay, I hope you can differentiate that. Now what happens is we have the outside, yes, 10, that is very explicit. And then you have the inside, t tan t. But remember, when you do the inside, you have two things there, right, which are being multiplied. So remember to use the product rule when you take the derivative of the inside. And so dy over dx will be 10 times t tan t power 9. So you took the derivative of the outside times the derivative of the inside. So you're going to use the chain rule. So if you're using chain rule, this could be your u and this could be your v, u prime v plus v prime u. So don't try to break it into too many steps. That way you don't lose track of all the different turning parts. But use different colors. At least that's what helps me to quickly account for them. In fact, it will be better if you use those colors itself do your calculations. That's one way to handle this, if you're a visual person like that. Okay, u prime v, so 1 times tan t plus v prime u. Derivative of tan is secant squared t times t. Derivative of v, so u prime v plus v prime u. So I'm going to show that here. U prime v plus v prime u. All right. I'm going to throw that in the front. So that's going to be tan t plus t secant squared t, right? And then I'll put this 10 in the front, this 10 here, that here, and then this t tan t power 9 right at the end. And that will be our answer there. Clearly, you can see one outside. This grand inside. So, instead of showing the whole thing, I'm going to show this as inside, because you will be actually doing the derivative of cosine. And then I'll show this as the innermost. Work from outside towards the inside, layer by layer. Okay, derivative of the outside will be cosine, and then write as you see the rest of it. Okay, times derivative of the inside. So derivative of cosine is negative sine, the rest of the things as you see it, times the innermost, the green, which is 2. Let's quickly make a reference here. And lastly, all right, now it's time to bring them all together. The negative, the 2, I'd like to put the sign first. There's no preference, I just like to put the more complicated expression right at the end. And that's our answer there. Okay, so I'm going to let you discover the outside and the inside. I'm going to work it out and then come back to explain it, so that there'll be a little suspense to check if our work is right, isn't it? So dy over dx Okay, let's see if you were tracking with me. Right, 3 was the outside. The whole thing is inside, yes, but we saw that in this whole thing inside, you had chain rule to apply when it came to tan. That's why you have that secant squared. Okay, this was the outside and the inside. So chain rule inside chain rule is what you see in this example. And then you had the innermost, t over 12 was the last one to multiply up there. Wow. The only thing I can see that simplifies here is this 3 and the 12. So you get a 4. And then this 4 here and this 4 will cancel off. So all the constants there are cancelled off. So that becomes basically, this is what your answer will be, dy over, I made the mistake again, dy over dx. No, it's dy over dt. dy over dt. But even though I tend to repeat that mistake of writing the dx, I do have an inbuilt system where I come back to check, and that's how I catch myself each time. So it just shows you that it's only human that we have certain preferences, and so we usually go by that. But have an inbuilt check to look at the previous step constantly, because as you see, these are complicated expressions. If you don't check them right away, and if you just, even if you check 2 steps later, it can be quite difficult to recover, meaning you'll have to go back and do it afresh instead of going back to fix that mess. And so that is my recommendation here. Again, there's no particular order in which you should be writing this, because they're all of different functions, totally different ones. So I just write it in this way. All right, let's go to the last problem. Okay. To make it a little interesting, we're going to find y double prime, second derivative. We're given y equals 1 over 9 cotangent 3x minus 1. So y prime will be 1 over 9, which is constant. Derivative of cotangent is negative secant squared x, right? So negative, not secant, cosecant. Derivative of cotangent is negative cosecant squared x. So I do the negative cosecant, but here again, instead of x, I have 3x minus 1. So I'll have to remember to use the chain rule. So the cot was the outside, and this was the inside. And so the chain rule allows me to multiply it by a 3. And before we take the second derivative, it's a good idea to simplify this. So my y prime is negative 1 over 3, right? Cosecant 3x minus 1. Oh, cosecant squared. How did I miss that? That was a big deal. Cosecant squared. Cotangent, derivative of cotangent is negative cosecant squared. Okay. We got that, and now we can do the second derivative. Once again, the constant can be kept outside, and we need to do the derivative of cosecant squared 3x minus 1. So here what you notice is this is your outside, because it's a power. Then this becomes your inside, and this is your innermost. Okay. So I need to work on the power first. So it's going to be 2 times cosecant of 3x minus 1. Power 1, so I'm not writing the power. Okay. So that's the derivative of the outside times derivative of cosecant x. derivative of cosecant x is cosecant x tan cotangent x. Cosecant x cotangent x. I need to quickly check if it was a negative or a positive. Let me check on that. Yes, that's a negative. So cosecant derivative of the inside, right? I'm doing the orange part now. So that's going to be negative cosecant x cotangent x. But instead of x, I have 3x minus 1. Leave the inside alone. So negative cosecant x cotangent 3x minus 1 times the innermost, which is going to be 3. This whole thing. So what you're beginning to see now is that it is a common occurrence to have chain rule inside chain rule, power rule inside chain rule inside power rule. So a complicated combination of all of these. So it only comes with practice, I should say. So do as many problems as you can, and that's one of the reasons why I'm showing you as many problems. What's really neat is that I'm able to afford all these problem types, because this really drives home what I'm trying to do here. Okay, I'm collecting all the numbers. Okay, the sign negative and the negative makes it positive. And then I have to collect all of these, right? So I have a cosecant 3x minus 1, cosecant 3x minus 1. So why not write it as cosecant squared 3x minus 1? Everything was matching. And then we have the cotangent 3x minus 1. The 3's here cancel off. Second derivative of y cleans up as 2 cosecant squared 3x minus 1 cotangent 3x minus 1. That will be the answer. Alright class, that was under an hour, very close. Thank you again for watching this video and working alongside me. I will see you in the next section of chapter 3.